Welcome to another episode of General Topology session, and today we will talk about the neighborhood and the interior of a set. So the first one, I will start with the neighborhood, which will go as follows. So again, we will start with a topological space, general topological space. Let X tau be a topological space. And we will say N is a neighborhood for a point neighborhood of the point P if the following is correct. So we have the picture, we have set N, and inside it we have a point P. When this is a neighborhood, if we have the following situation, if there exists an open set U such that, first of all, the set U should contain the point P, should be of course open, and it should also belong as a whole in M. In this case, N will be called a neighborhood for the point P. So this is the first definition we have today. Let me go ahead and let's see some examples from the famous topology that we have seen so far. So example number one, we have the following. The closed interval, I will take the closed interval from 0 to 1, which a part of the real number and the Euclidean topology is a neighborhood to the point half, for example. And why this is true? Because if we draw the number line up to here, this is 0 to 1, and this is my point half in the middle. Now the question, can we find an open set U that contains half and live inside the interval 0, 1? I think that's easy. We can set up U to be, for example, this is just an example. We can take U to be the interval from 1/4 to 3/4. Now, this U will contain, of course, the point half is inside this U, and the whole interval lives inside the interval 0, 1. So this is exactly a neighborhood for the point. Of course, there are many other neighborhoods for the point half, but for now, we just want to find one neighborhood. We call it N, and this is the neighborhood up here. Now, let's see another example. Example number 2. And this time, I will choose the interval that starts from 0 open to 1 closed. Again, in the Euclidean topology of the real number. Of course, this is not a neighborhood for the point P equals 0. This is not. Now, how do we prove it? First, if we try to visualize this, my point will be exactly here. Any open set would just be a little to the right of the 1. It will go outside the neighborhood, outside this interval. So this will not be a neighborhood. Now, if we can just relate the idea of the neighborhood in the third example, example 3, it's a general example. Any open set U is a neighborhood for the point B in U. So U, if it's open, it's already automatically neighborhood for any point inside the U. The same concept can also happen if we have a basis. So if we have a basis, then the same story will go with the same idea. So a basis is a neighborhood. The basis set B is a neighborhood of every point in B. And that's exactly, or that's mostly what I would like to mention about the neighborhood. So the idea of the neighborhood is we have a point and then we can find an open set containing this point, and the open set itself is contained in what we call it the neighborhood. Now we will go to the second part of this lesson, which I want to talk about the interiors of assets. So here, the interior of assets, and this is very important topic. And let me start first informally explain to you what is the interior of set. So again, we will start with a set. We will call it A, and then I would like to look inside A. Now focus inside A, and I want you to find the open set inside A. So find all the open sets inside A. One of them should be the largest one. And that largest one, that largest set which contains inside A, this is what we call it the interior. So here we have the interior is the largest set inside A. We call it interior. Now, if we want to define it, it will be defined as follows. We will say A interior is the union of all open subsets contained in A. So take all the open subsets inside the A, take the union of them. What we will get, of course, is the largest set, and this set we will call it A interior. Of course, from the definition, we know that A interior is subset of A. Now, let me just write a couple of remarks about the interior. We'll keep them on track here. The first one, as we just mentioned, A interior will be, of course, still less than A because it's the largest. It's the union of all open sets contained in A, and their union will still contained in A. Number two, the interior is open subset. And why this is true? Because it is a union of open subsets. And because we have a topology, any union, any arbitrary union is again open. So A interior will be also an open subset. Number three, which is one of the important ones, is A interior is the largest open subset contained in it. And that makes sense because from the definition of the interior, it is the union of all of them. The union will just make the subset, the result will make it the largest one because I'm putting all the open subsets. So we have this definition here. We have alternative definition. Either you can say the interior is the union of all open subsets contained in E, or you can say it is the largest open subset contained in E. And we have a third way of saying about the interior, and this one I will write it in blue because I want you to focus on it because it's very important to use it whenever we need. Now, what does it mean X belongs to the interior? It means that, of course, if X belongs to the interior and the interior is just a union of open subsets, it means there exists an open subset U such that X lives in U, and of course U is always contained in E. So we get this story. It means if you take something in the interior, you get definitely an open set containing that point, and everything will stay inside A itself. So that's what we have. I prefer now to pause for a second, maybe do a quick example, and then continue the list of the remarks here. So just let me go ahead to the next example. Example 4. The usual example, let X be a finite topology consists of A, B, C, D, E, and the open sets are the empty sets X itself, A, C, D, finite topology, A, C, D, and finally B, C, D, and E. Those are the open sets, and the question is we want to find the interior of A if my set A is just A, B, and C. We want to find the interior, so let's see the solution. Of course, here we have many ways to solve this example because we have three definitions, equivalent definitions for the interior. Either we find the union of all open subsets contained inside A, or we find the largest open set contained in A, or we try each point of this topology whether it lives in the interior by finding an open subset containing that point. Of course, looking visually on the largest subset will be the easiest option. Now, those are the open sets. They are in a list in front of me. I just need to choose the largest one that completely lives inside A. And I think that it's clear that A dash is the largest open subset contained in. And of course, if we go through them one by one, of course, this will be eliminated because it doesn't contain in A. We have B making a problem. This is eliminated. This is again eliminated. So we have only those three options. Among them, all of them, at least this is also eliminated. Only we have two options, the empty set or this set. Which one is the largest? It's this one. So the final answer will be just. And that's how we find the interior. Now, if we do another example, this time we'll do the example from the Euclidean topology on the real number. Let A equal the set 0, 1, the closed interval 0, 1 in the Euclidean topology of R. Then the interior, which is the largest open subset, of course, as you expect, it will be just the interval from 0 to 1 without the endpoints because we need it to be an open subset. And the open subsets in the Euclidean topology are intervals or union of interval, and the largest one, the largest interval that can be in E is this one. So here is the interior. We go back to the remark. We stopped at remark number 4, and now we will do remark number 5, which as follows. A is open if and only if A is equal to its interior, which makes sense because remember, A interior is the largest open subset. Now, if A is open, it means A is the largest one. So they are equal. And of course, if they are equal, we know this is open, so this will be also open. So it is if and only if in both ways, and we can use it to prove the following. Now, what is interior of the interior? That's a good question. If we do it step by step, this one is open. Now, the interior of open doesn't change. It is the same if it is open. Now, A might not be open, but the interior as a block is open. This is something open. So whatever inside will stay inside, and the answer will be A. Those are a couple of remarks. We would like just to pause the video for a minute, look at them, think about them, make sense to you, adjust to the 6 remarks in addition to the definition of the interior. Okay, what we'll do next is we will prove a nice proposition which will tell us lots of information about the interior and its relation to the subset, its relation to the intersection, and what happens with the union. So let's start with the first one. If A is subset of B, then the interior of A is a subset of the interior of B. We want to prove that statement, and in order to prove it, we will assume A is subset of B. Then we will look at the interior of A, which is the union of all open set U. U is open, and U is subset of A. Now, U is open. That's a good news. Now, U is subset of A, but we know that A is also subset of B. So everything here must live in the bigger collection of all the U that live in B, and that's exactly the interior of B. So the interior of A would be just a subset of the interior of B. Why? Because U is subset of A, and A itself is subset of B. So B has more open sets than the one in A, which results as the interior of A is subset of the interior of B. So this is the first one. Now, for the second part, is we can use a little bit of a shortcut, because here in the second part we need to prove that this set is equal to the right hand side set. So we have to prove that each set is subset of the other. So number 2. Okay. We know those two facts: the intersection subset of A and the intersection subset of B. Now, by 1, if we apply number 1, the interior of the left hand side will be subset of the interior of the right hand side, which is A intersection B is the subset of A, and the second one will be the C. So collectively speaking, if we put all those together, what we will get is the intersection, the interior of the intersection lives inside the interior of A, at the same time lives inside the interior of B. So we finish from one direction that the interior of the intersection is the subset of the interior of each one of them. Now, conversely, now to prove the other direction, I will take an X which lives here, and I will prove it lives in the interior of the intersection. So conversely, let X in A interior intersection B interior, which means that X lives in the interior of A, and at the same time, X lives in the interior of B. And this has a meaning. Let's see what's the meaning for each one of them. So X lives in the interior of A has a meaning, which means there exists U1 open with X in U1, and U1 is in A, and X in the interior of B means the same thing, but a different open set. There's this U2, again open, where X is in U2 and U2 is subset. Now, I find X in U1, I find X in U2, U1 lives in A, U2 lives in B. If I want X to be in the intersection, I must take the intersection between U1, take U equals U1 intersection U2, which is open. So X will be in U, and of course U will be subset of A intersection B, which means X is in the interior. And that's exactly what we want to prove in part 2. Hence, A interior intersection B interior is some set of A intersection. And that's how we do that. The next one, and number 3, is something about the union. Which we want to prove that the union of each one is subset of the interior of the union, and this is we will do it again using part A because we know this information. So by 1, the interior of A will be subset of the interior of the union, and if we do the same thing for B, we get the interior of B which means if we take the union of this, it will live, of course, in the same place here. So if we take the union, we'll get this one. Now, why we can't prove that those are equal? So let us see an example of two sets where this is not an equal. So let me just do example 7. I want you to try to take A to be the set from 0 to half and B to be half to 1. Now, if we do A interior union B interior, this will give me the following. It will give me the open interval 0 half union half 1, which is as a whole will just give me the interval from 0 to 1 except of half, because half is not included in both of them. However, if we find the union and then we take the interior, the union will be just 0 to 1, and if we find this one, will be the usual interval from 0 to 1, and this shows that they are not necessarily equal. One of them is subset of the other, but they are not equal, which shows that number 3 is just a strict subset. We can't make it equality. Next is we want to explore some of the relation between the interior and the closure. So just if you allow me here, I will just write relation between the interior of a set and the closure. So it is a good practice if you can now pause the video and remind yourself of the definition of the closure. For the definition for the closure, maybe it's a good practice if you pause this video and go and see what is the definition for the closure. Now, this proposition says that the interior of a set is equal to the complement of the closure of the complement. It's a little bit tricky. It's a complement of the closure of the complement. And we want to prove this one. This will help us a lot later on. If we know the closure, we can know the interior. And if we know the interior, we can know the closure in an easy way. So we want to prove this one. Of course, how we prove that two sets are equal, we'll take an X here, and we will try to show it's there and vice versa. So first of all, I will let X be in the interior, and which means if we do for the practice to have this one, and then this is X. So I will take X in the interior. So it means there exists a U open subset such that X in U and U is in U. Something like this. This is U. And U is open. Now, to prove this one, I will use proof by contradiction. So I will assume X does not belong to X AC complement, which means I will assume X belonging to the closure complement, which of course has two options. Option number one, X is in AC, and option two, X is an interior, is a limit point for this. Of course, X in AC, this is a contradiction directly without doing anything, because we assume from the beginning that X is in the interior, hence X is in E. So we get a direct contradiction. X cannot be in the complement at the same time as the set A. On the other hand, let's assume that X is not in the complement, but it is a limit point to the complement. Now, a limit point to the complement, it means for any open set, to remind you of the definition of the limit point, for any open subset, let me call it O, that contains X must contain a point of the complement. But again, this is a contradiction. Why a contradiction? Because we have U, an open set that contains X, but U does not contain any point from the complement. Why? Because U is subset of A. It lives inside A. It has nothing to do outside A. So we get in both directions, we get a contradiction, and this is the first part of this one. Okay, now let's do the second part. Now let me take an X which lives here and I try to show it lives in the interior. Now, the second part, let X belongs to X except the complement closure. Hence, X is not in the closure of a complement, which means X is not a limit point and X belongs to A. Because something not in the closure, it means it's not in the A complement or a limit point that complements. So limit point of A complement. Hence, we must find an open set U that contains X, which does not contain anything from the complement. Does not contain anything from the complement. Hence, X will be in U and U will be in A. Therefore, X is in the interior. And that's the proof of the first theorem that will give me the relation between the closure and the interior. Now, let's go to a small and easy corollary about the dense set. So here we say A is dense if and only if the interior of the complement is empty. So this means there is no open set inside the complement. The complement is very shallow. There is nothing as an open set there. How do we prove it? We just go with the definition of a dense. So A is dense if and only if X equals the closure of A. Which means if we take X, we get an empty. And that's clear. Now, if we apply the previous proposition, look at the previous proposition, but don't look at it as A, switch A and A complement. So before this was complement, now I don't have complement. What is this? X except the closure, it is the interior of the complement, which is, and that's exactly what I want to prove. It's a very nice proof, very simple, but just look at it and put things together, you will see it. So finally, we reach the end of this lesson about the interior of a set. But at the same time, we felt that the interior is somehow similar to the closure. There are similarities. There are something to be summarized. And that thing is be given in the speech. First of all, we know that the interior of a set is open. We know the closure is closed. And we know that A contains the interior and contained in the closure. So we have interior inside A and A inside the closure. Now, the interior is the union of all open sets contained in E. If you remember, the closure is the intersection of all closed subsets that containing E. So one of them is the largest one, largest open set, and the closure is the smallest closed set containing A. And that gives you the idea of you have A, inside it you have the interior, which is open, and in the above you have the closed. So this is kind of asking you, if I give you a set A, you are telling me what is the next closed subset will be the closure, and the previous open subset, which means inside it, is the interior. Thank you very much for watching. I hope you enjoyed this video.